In this video, we're going to use the results of the prior delay time stack video. We have a delay time solution, and we're going to use that to make first break picks. So go over here to displays, picker, the standard picker. And again, you really need multiple monitors to get the full benefit of Phoenix. But for now, we're just going to open it in the tab display. All right, let's go ahead and select pretty much any shot. And then we're going to move out the delay time solution. This will actually do several things. It will remove traces which are not inside a branch, and it applies the solution. Okay, I'm going to left click and drag again on the time axis to zoom in so we can see what we're looking at here. And you can change the display. If you got too many traces on the screen, Phoenix by default goes to this grayscale. But you can change that so that you can actually see the wiggles pretty easily. And if you zoom in, you can see even more wiggles. That's fine. Okay, let's go ahead and add the pick event nearest time, just like Flatirons. And if you click around the survey, you can see how things look. I'm going to go ahead and zoom in on this again. Some shots have pre-existing user picks. We don't really care about those. We're not going to use them. They came from when we imported this project from Flatirons. Okay, so it looks okay. Let's go ahead and make batch picks using this solution. You simply click Launch Batch, Run on Local Machine. If you got a giant survey and a cluster is available, you can run it using MPI. But first break picking tends to be I/O limited, so you're not going to gain a lot by more computing power. Let's click on Launch Batch, and we'll just use 8 threads. That's all I can do on my laptop. And you click on OK. And this is going to run in branch for a minute or two, so I'm going to pause the recording. The batch pick job has finished. One thing I'm not showing you is that while you're doing these batch jobs like stacking or picking, you can actually be using Phoenix to do other things like other aspects of the same project or work on different projects, unlike Flatirons, which basically locks the application. Okay, so we click on OK here. And the next thing we're going to do is use these picks to compute a solution. In Flatirons, it prompts you to copy the nearest time picks to the user picks. You don't have to do that in Phoenix. You can actually directly use the nearest time picks in the solution. All right, let's go back to our delay time tab. And I'm going to show you this more later in other videos, but you can have any number of delay time solutions open at one time, unlike Flatirons, where you have one active version. It's a lot more flexible. You can do more comparisons. You'll love it once you get used to the confusion. All right, we go to the Analysis tab, and we're just going to do the standard analysis sequence. This is very similar to the option available in Flatirons. Be sure to pick the correct pick version. It's really easy when you're busy to skip this. And the defaults are almost certainly going to be fine. By default, you have this linear compression turned on. I find that helps avoid edge effects. If you want, you can turn it off. It'll be more direct comparison to a Flatiron solution. You click on OK, and this is actually going to run fairly fast. It just takes a second to, it's only 9 million traces, so, and unlike Flatirons, it took about 10 seconds. Phoenix does a couple of things. The delay time is threaded, so it's much faster, and it will look at the size of your survey, and if it's not too large, it keeps the picks in memory. So it can be blazingly faster than Flatirons by quite a bit. Okay. Here we go. Now we can go to the map view and look at our solution. I'm going to make the dots a little bit bigger here. So here's delay time 1, delay time 2, and our velocity fields. They're very smooth. Okay, you can do some QC. Click on the Pick QC tab and just click shots. And you got to be sure to select the correct pick version up here. You can't really see, but in the top plot, the red dots are the nearest time picks, And the blue dots are predicted by the delay time solution. You can see they're essentially on top of each other. Second plot down is a difference plot, user minus the, or not the user, the nearest time picks minus the predicted. And you can see the error is quite low. And the bottom plot is the error plot, but plotted with azimuth. This plot, the bottom plot, will show you if you have a lot of anisotropy. And you can see that there's very little anisotropy in this survey. All right, so the PIC-QC looks fine. You can actually color it by the error terms, and if you've got high error someplace, you can go check it out and figure out why. Maybe you've got geometry or polarity flips. Okay, the next thing we have to do is create a model, and there are a number of options. The most common one is you just assign a weathering velocity. So this is the velocity of the shallowest refractor, about 14,000 feet. So I'm going to choose half of that, 7,000 feet per second. You click on OK. That runs pretty quick. And then you can go to profiles. And just like flat irons, it looks exactly like flat irons. You can look at some profiles. And then you can decide how you want to compute the statics. It's very simple. You'll see the same button in every window. So the refractor 2 elevation range is minus 2251. There's a bug. There's actually a geometry problem in the survey. So I'm not going to compute statics now. We have to go back in another video and fix that. So I'm going to cancel. Let's say you want to compare different ways of doing the modeling. Like you might be a fan of using a flat refractor surface for modeling, or any other number of approaches. The easiest thing to do at this point is simply click on Clone this solution. When you do that, it's going to make a copy of all the delay times and the refractor velocities and the branch in a brand new solution. We're just going to do it. We'll call it 2layer_clone. By default, that's the name it comes up with. And we'll open it in a new tab. And here we are. Now we can do a different kind of modeling. Assign weathering velocity 3,000 instead of 7,000. And then when you come over here and do the profiles, you can go back to this window and see how those profiles compare. So that's really all there is to doing a delay time solution in Phoenix. It's actually very simple. Now, one thing I want to show you before we quit the video is there are two types of analysis. The standard sequence, which is very much like flat irons, and then there's using gridded velocities. In this survey, we have seen dramatic improvement in the statics coming out of this, and we've seen other surveys where the statics are not any better at all. So I do recommend trying this solution because it's fairly fast. Let's cut the smoothing down to 33% of the max offset, and nearest time, we've got that correct. And we're doing nonlinear compression on the refractor velocity fields. Really recommend that. You can get some great results. I shouldn't say great, very interesting looking results by doing this. I'm going to click on OK. This takes a bit longer to run, so I'm going to pause the recording. All right, the gridded velocity analysis is finished. Let's go ahead and take a look at it. Let's go to the map view and display gridded data. Velocity number 1, and we can go to the clone and look at the same thing, velocity number 1, and you can see just a huge dramatic difference between the two velocity fields. This survey is deeply uninteresting. On some surveys in fill zone areas, for example, you can get just a dramatic difference in the two solutions. And so again, Phoenix, it's very easy to create new solutions, delay time solutions, have them all open at once and do comparisons. The analysis is super fast. So I really recommend trying a number of different things within Phoenix.